Hello friends, good morning. Yes, so today we have to discuss about the free radical in reaction mechanism. Okay, this is the paper of semester fourth or third. Okay, semester third in MSc Organic Chemistry, and the name of paper is reaction mechanism and biogenesis. Out of that, we have already covered the biogenesis part, and now we are going to start the section first, which is reaction mechanism, organic reaction mechanism. So in this reaction mechanism, the first part is which is methods or determination of the reaction mechanism, uh, all which is related with the free radical mechanism. So let's begin with that. Okay, I would like to share my PPT. Okay. Yes, I think you can see the my PPTs. Okay, so free radicals in organic synthesis. Uh, you can take the help of this textbook, which is the Claydon, which is well known for us. Then I will use this pointer having color. Better I will keep blue color and the size. Can I change the size? Okay, anyway, I cannot. So we'll start with the free radicals. In this, what you will learn is importantly, first, what do we mean by the mechanism of reaction? Then we'll learn the ways to determine mechanism of a reaction. Also, we'll understand or identify the reactants, products, and intermediates involved in the reaction. And again, how to evaluate the steps involved in the reaction. That was the learning outcome, the design by the university, which is Savitribai Phule, Pune University. The first point, which is heterolytic fission. What is meant by heterolytic fission? See guys, if a bond breaks in such a way that both electrons remain with one fragment, the mechanism is called as heterolytic, right? Which is means not a symmetrical way. Okay, hetero means unsymmetrical, you can say. So we'll take one example. Suppose we have HCl in presence of water. What will happen? H will become a positive charge and chlorine will become a negatively charged. So how many electrons will remain with hydrogen? Are 0 electrons. And what about the chlorine? Chlorine will gain 1 electron. So in outer shell, chlorine will have 8 electrons. Okay, and with the help of water, both will stabilize. This H will react with H2O and you will get it H3O. When bonds break and one atom gets both bonding electron pairs of lones driven by the energy of solvation. Okay, why this bond will break? Because of energy of solvation. This HCl would like to uh, make a bond with water, right? So this is the one possibility. Then what about the homolytic fission? If a bond breaks in such a way that each fragment gets one electron, free radicals are formed. Now this the picture will start with free radicals. See, the free radicals are formed and such reactions are said to take place by homolytic or free radical mechanism. Means free radical mechanism means homolytic fission. Okay, so please note in your notebook, free radical mechanism is nothing but the homolytic fission. Then only this reaction will be uh, processed. Then for this less energy demand, okay, less energy demand will be there where I am writing now. Okay, so see, again we have taken this HCl, and rather than at one side there will be homolytic fission. This bond will break in such a way that one electron will remain with hydrogen in gaseous phase. This phase is also important. Okay, and one electron will remain with chlorine, because the bond between hydrogen and chlorine will prepared by two electrons, right? So 7 electron in outer shell and 1 electron in hydrogen outer cells. So this is monoatomic radicals. So when bonds break and the atoms get 1 electron each, this is homolytic fission. Okay, understand how free radicals will be formed. Next, the application. Actually the pericyclic reaction mechanism. Now this is the, I can say, the application. In this type of reaction mechanism, the electrons move in a closed ring and there are no intermediates. Pericyclic means no nucleophile, no electrophile, no intermediates, no ions, no free radicals. And it is impossible to say whether the electrons are paired or unpaired. So how this reaction happens? I think we have already covered the pericyclic reactions in first semester of MSc Organic Chemistry. So there we have already enjoyed. Without reaction mechanism, we have learned this paper, right? So, so how this happen? So we'll see some example. And now the how then this reaction will proceed. So radical formation, or we can say this is initiation reaction. Initiation reaction. There are two methods. One is thermolysis, another is photolysis. If you remember thermolysis, how we used to show like this, and photolysis, how we used to show this quanta energy. Yeah? These two terms which we have already learned in the pericyclic, right? So light is a good energy source, which is photolysis. Which light? There are three types of light. Red light means there are 167 kilojoule per mole energy. Blue light means 293 kilojoule per mole energy, and UV light having lambda max values, which is 200 nanometer, or we can say efficiency of UV light is 200 nanometer. Then the energy will be energy source is 586 kilojoule per mole, which is too high compared to this. So ultraviolet light will therefore decompose many organic compounds, right? And practically we can see if any compound or any plastic compound or any material, if we have kept in its sunlight, okay, or not only sunlight, we can say the bright sunlight in afternoon or for few days, automatically the color will be changing. We can observe it in for the vehicles also, some cloths and all plastic accessories and other things also. Okay, so there is a decomposition process, and because of decomposition you can find it there will be some reactions. Okay, suppose in that uh, compound we have Cl2, and if we have used the light on Cl2, what you will get is there will be radical formation. There will be radical formation, and the energy required for that is 243. What about for bromine? To form a bromine radical, the minimum energy will required compared to the chlorine. And to form the iodine radical, again we need a less energy, right? Maybe then in other way we can say that chlorine-chlorine bond is stronger than the iodine-iodine bond. Okay, in other way around we can discuss on that. Now our target is how to form the radical and how much energy will require for that. And without the radical formation, the reaction will not start. So that is initiation process. So initiation process is the formation of radical ion, and there are two catalysts or only two ways. One is thermolysis, another is photolysis. Right? So write down the basic behind it. So we'll take one example, right? This example, which is well known for you. Just okay. See, application of mechanistic understanding to help to control product yields is also of commercial significance. The addition of HBr to alkenes, which may occur via cationic or radical mechanism. Pure alkene, alkenes in the absence of peroxide react to give the 2-bromo product, which is Markovnikov oxidation, and in presence of peroxide or other radical sources there will be a anti-Markovnikov oxidation, gives 1-bromo products. Guys, hope you remember this type of compound. Suppose we have unsymmetrical compound which is RCH double bond CH2, and we are adding HBr on that. Okay, if there is no peroxide, okay, means no radical type of reaction, then we will get the 2-bromo type of product. And this 2-bromo product, how you will get is Markovnikov rule, right? Markovnikov, or in short we used to write is MR rule. Okay, MR rule. And if we have used the trace of peroxide, suppose there will be a peroxide mechanism, then due to the stability of radical formation, so there will be 1-bromo type of product. Why this is happening? See, in this first reaction, there is okay. In this first reaction, there will be a formation of RCH, right, CH3, and there will be a positive charge. And this positive charge is stable compared to RCH2 CH2 carbocation. Means this is primary carbocation and this is secondary carbocation. Okay, so secondary carbocation is more stable than the primary carbocation. Okay, so due to the secondary carbocation stability, you will get this 2-bromo type of product, right? And here in this case, what will happen? In this case, there will be no carbocation formation. So in second case, there will be a formation of free radical. Free radical. Okay, and due to this free radical formation, you will find this 1-bromo type of compound or products, all products, Right, so you can take one example and write down the mechanism. Another example is the mechanism of chlorination of methane, which accounts for the formation of a small amount of ethane along with chloromethane, dichloromethane, trichloromethane, tetrachloromethane, and so on. See here, we have a methane, okay, and if we have used this chlorine, how much light we have passed, based on that, there will be formation of chloromethane. Again, there is a possibility of again some quantity of light which we can use. There will be formation of CH2Cl2, dichloromethane. Again, is very difficult to control. Okay, again we have used this light, or we can write down H nu. Then there will be a formation of chloroform, and again we can prepare it up to carbon tetrachloride, okay, or tetrachloromethane. Anyway, you can this one, okay. So this is again the mechanism, is how this reaction will happen. Initially, when we have the chlorine bond in presence of light, there will be formation of carbon radical, okay, and due to this radical formation you will get this such important compounds from the methane. We'll see the another example. Yes, I think this reaction is also familiar to you, which is Hofmann rearrangement reaction. And in this Hofmann rearrangement reaction, there will be amide initially, and amide gets converted to amine, or we can say the primary amine. So in the mechanism for Hofmann rearrangement, the carbon is lost as a CO2. Okay, and there is again the formation of a radical ion in the Hofmann mechanism. And there, how the radical is initiated, you can see this NaOBr. Okay, so there will be formation of a radical, right? So in this reaction also you can find the free radical reaction mechanism. The next example we can discuss about, other than there is an example, but there is, we have discussed about the product stabilities and kinetic and thermodynamic control of product formation. So what is thermodynamic control? Which is related to temperature, right? And what is kinetic is related to speed, right? So the initial product of a reaction are formed under kinetic control. However, subsequently the products formed are governed by thermodynamic control. So kinetic control as well as thermodynamic control. When a mixture of 0.01 molar of each of cyclohexanone, see the reaction initially. There are cyclohexanone, which is 7 number, okay, and there is a mixture of this furfural. Actually, this is furan having one aldehyde group on the position, so which is furfural. So when furfural and this cyclohexanone will react together, there will be a formation of semicarbazole, right? So this is 9 or 10, okay, semicarbazole, and yes, so second was cyclohexanone, semicarbazole, uh, initial kinetic control, but after few hours the product was the semicarbazole, subsequent thermodynamic control. So see, in few seconds means there will be kinetic control. Few seconds means the kinetic control, and what you will get is this product. Okay, and in thermodynamic, after few hours, see the reaction condition here. This is few hours and here few seconds. Okay, so here there will be addition on this carbonyl, and after few hours there will be addition on this carbonyl. So kinetic and thermodynamic products from equimolar amounts of cyclohexanone, furfural and semicarbazide. Okay, so this is the best example to understand what is the product stability, kinetic and the thermodynamic control, right? Again, we'll discuss about the very important and well-known reaction for all of us, which is pinacol-phenacol rearrangement, right? So we have an benzophenone, and benzophenone is the very good initiator. Okay, if we have benzophenone in presence of light, okay, there will be excitation. So this is the logo of excitation, the star mark. So means whatever electrons present in this carbonyl group, they get the excited from singlet to triplet. Understand? And what will happen? So excited triplet or biradical formation, and there will be formation of this one. See, so the two molecule of this benzophenone, one molecule will have these two radical, and another molecule will have, because see, the one hydrogen from here it will out, another hydrogen from here it will out. The two hydrogen will get attached to this carbon. Okay, so this is biradical or benzhydrol type of compound you will get, and then there will be hydrogen abstraction and the stable radical you will get it. And this stable radical, why this is stable? Again, this is tertiary type of free radical, and both these radical will combine together and you will get the benzphenacol type of compound. Okay, so when these two compounds will combine together, there will be formation of benzphenacol, right? So this is phenacol formation reaction using free radical. If we have an peroxide, what will happen? In photochemical reaction, there are some reactions in presence of peroxide it will happen, rather than benzophenone now. So see, this is the peroxide, well-known peroxide. This is the linkage of peroxide COOO. Okay, you can see there is a homolytic fission, and there will be formation of RCOO radical. Okay, the two molecules are there, and there will be a decarboxylation, means minus CO2 will come out, and there is a possibility of another radical, which is R radical. And when R is alkyl, loss of CO2 is very fast. When here R is alkyl, loss of CO2 is very fast. Therefore, alkyl peroxides generally avoided, as they tend to be explosive. Understand? Because if we have used this alkyl peroxide, then there will be explosive type of reaction. Okay, means suddenly it will react. Okay, so very difficult to control. But many times what people use is benzoyl peroxide, because benzoyl peroxide has a half-life of 1 hour at 90 degrees centigrade. So this benzoyl peroxide compared to alkyl peroxide is mild and which is stable and useful. So as it selectively decomposes to benzyl radicals below 150 degrees centigrade. So what we will suggest is R should be always benzyl. Okay. So I think we'll stop for the first session, and next we'll see how many the peroxide initiator are there. And this is DTBPO is the peroxide initiator. Then this is azo initiator, which is very famous, AIBN, azobis isobutyronitrile, and so on. Okay guys, so let's see in the next session.